Hello everyone, we are Team Europium, and in this video, we'll explore the basic inorganic reactions of representative elements. For the outline of this video, the brief introduction to representative elements that will be discussed by me, Gerard Banaag. Next, the properties and basic inorganic chemical reactions of representative elements, which will be discussed by my groupmates Ron Estrella, Jez Quizana, Diana Mayor, and Nicole Vidal. Make sure to listen, take notes, and answer the questions throughout the video. For the introduction of representative elements, or also known as the main group elements, are composed of those in the S and P blocks of the periodic table. Also, this group is made of metals, nonmetals, and metalloids. Let's start exploring the basic inorganic chemical reaction starting from Group 1A, Group 2A, and Group 3A through 7A.
Hello everyone, I'm Ron Joseph Estrella and I'm here to report about the Group 1A elements. The element Group 1A is composed of hydrogen and alkali metals. Now let's talk about alkali metals first. Alkali metals is composed of lithium, sodium, potassium, rubidium, cesium, and francium. They are also known as S-block elements due to their highest energy electron in the S subshells. Now they all have one electron in their outer shells, allowing easy obtaining of a full outer shells by losing their outer shell's electron in reaction to form positive ion with a +1 charge. Unlike typical transition metals, alkali metals are soft, low density, float on water, and have low melting and boiling points. They also share properties with typical metals such as being a good conductor of heat and electricity and shiny when being freshly caught. Now let's talk about the trends in alkali metals. Down the group, there's an increased atomic radius due to the extra electron shells. There's also an increase in reactivity due to the larger atom size and full electron shells. But the first ionization energy and electronegativity decreased due to the increased shielding between nucleus and outer electrons. There's also a decrease in melting point as ion grew larger. But there's also a decrease in density of alkali metals down the group, but this trend is not perfect due to the less denseness of potassium than sodium. Now let's talk about the reaction of alkali metals with water. All alkali metals react readily with water and the reaction becomes more vigorous down the group and creates a lot of heat. This reaction creates alkaline hydroxide ions and the reason why group 1 elements are called alkali metals. This is the general equation of the alkali metals reacting with water, where X is any group 1 metal. Now, in these following descriptions, a very small portion of the metal is dropped into the large container of water. It shows that lithium floats in water, emitting hydrogen gas and forming a colorless solution of lithium hydroxide, and sodium melts quickly in water, forming a silvery ball. Potassium reacts faster than sodium and igniting hydrogen. Rubidium sinks due to its density, forming a hydroxide solution and hydrogen. Cesium explodes in water, forming cesium hydroxide and hydrogen. Now let's talk about the reaction of alkali metals with oxygen and chlorine. First, let's talk about the reaction of alkali metals with oxygen. Alkali metals react with oxygen in the air to form metal oxides, causing tarnish. The reaction speed increases with the group necessitating storage out of air, and the less reactive metals like lithium, sodium, and potassium are stored into oil to prevent oxidation. Now, alkali metals like lithium, sodium, potassium, and rubidium produce colored flames with oxygen. Now, let's talk about the reaction of alkali metals with chlorine. Alkali metals ignite when heated and added to chlorine, forming metal chloride. Group 1 elements react similarly to oxygen, forming a white solid and simple metal chloride. Now, let's talk about hydrogen. Hydrogen has a very simple structure and the most abundant element in the universe. Hydrogen is a nonmetal with a ns1 electron configuration and above alkali metals due to its cation formation. It also has a higher ionization energy than lithium and forms hydride anions and dihydrogen. It can also be activated by heat, radiation, or catalysis, reacting quickly and externally with many substances. It reacts with active metals to form ionic hydrides and nonmetals to form polar covalent bonds. And like the group 1A elements, hydrogen has an outer electron configuration of ns1, has a single valence electron, and has a common plus 1 oxidation state. But unlike alkaline metals, hydrogen shares electron with nonmetals rather than transferring electron to them, and has a much higher ionization energy than any alkaline metals due to its small size. Now, so why isn't hydrogen included in alkaline metals although it has one electron in the outermost shell, just like the alkaline metals? Now the reason why hydrogen isn't included in alkaline metals is because hydrogen is a nonmetal and forms covalent compounds with nonmetals. Now let's talk about the group 2A elements. Group 2A elements are also known as alkaline earth metals. Just like alkali metals, they are also called S-block elements. But the difference is that they have two electrons in their outer shells. Now, just like alkali metals, alkaline earth metals is also silvery, white solid, and soft. They also have low densities, electron affinities, and electronegativities. But unlike alkali metals, they have higher melting and boiling points. Alkali earth metals has the same strength of alkali metals. Now, progressing down the group, the melting and boiling point decrease, and also ionization energies also decreases, while the densities, atomic radius, and reactivity increases down the group. Now, let's just talk about the alkaline earth metals reactivity. Let's start with its reaction with water. As you can see, the reactivity of alkaline earth metals increases down the group. It starts with the beryllium doesn't react and magnesium reacts very slowly, calcium reacts steadily, strontium reacts fairly, and barium at the end reacts rapidly. Now in the general equation for the reaction of group 2 elements with water is that the group 2 metal plus H2O will result in metal hydroxide and hydrogen gas. Now let's talk about the reactivity of alkaline earth metals with oxygen and chlorine. When it comes to oxygen, the alkaline earth metals form a metal oxide, and the general equation for this reaction is that group 2 metals plus O2 will result in metal oxides, as stated earlier. And when it comes to chlorine, the alkaline earth metals form metal chlorides, and the general equation for this reaction of group 2 elements with chlorine is that group 2 metals plus chlorine will result in metal chloride. And the reaction of chlorine are more vigorous than with oxygen. Why is the term alkaline used to describe the group 2 elements? The name alkaline is from slight solubility to water, while earth is derived from its inability to decompose when exposed to heat. Alkaline earth metals are named for their basic behavior and position in the Earth's crust.
The next would be the group 3A elements. The characteristics of the elements in group 3A vary significantly from top to bottom of the periodic table. The first member of group 3A, boron, is a metalloid and the rest are metals. In their highest energy orbitals, group 3A metals have 3 valence electrons. They ionize to create a plus 3 charge and have a higher ionization energies than group 1A and 2A elements. The group 3A metals have a silvery appearance and, like all metals, are good electrical conductors. They have lower melting points than several of the group 2A metals, making them comparatively soft metals. Most laboratory glasswares contain boron, which prevents it from shattering when heated. Boron does not form binary ionic compounds and is unreactive towards oxygen gas and water, while the following element, aluminum, readily forms aluminum oxide when exposed to air. Aluminum forms tripositive ions, and the group 3A metallic elements, gallium, indium, and thallium, form both unipositive and tripositive ions. Moving down the group, we find that the unipositive ions become more stable than the tripositive ions. Unlike groups 1A and 2A, none of the group 3A elements react directly with hydrogen to form hydrides. The halides of boron, aluminum, and gallium will react with sodium hydride, however, to form tetrahydroanions, such as given in the equation below. The compounds do not contain hydrogen ions. Instead, the hydrogens are covalently bonded to the group 3A atom. All these anions are tetrahedral, as would be predicted by the Vesper theory. All the group 3A elements form trihalides, although thallium does so reluctantly, preferring to remain in the +1 oxidation state. The general reaction is given to the right, where M are the group 3A elements and X are the halogens. An example is the reaction between aluminum and bromine, where after the reaction between the two has occurred, it yields aluminum bromide. The metallic elements in group 3A also form many molecular compounds, like aluminum reacts with hydrogen to form aluminum hydride, which resembles beryllium hydride in its properties. From left to right across the periodic table, we are seeing a gradual shift from metallic to nonmetallic character in the representative elements. For the sample question, is the first ionization enthalpy of thallium greater than aluminum? The answer is yes, as this trend is observed due to poor shielding of d and f orbitals. Gallium is smaller than aluminum due to poor d shielding, therefore the first ionization enthalpy of aluminum is less than the first ionization enthalpy of gallium. Similarly, thallium has an intervening f orbitals, which are very poor at shielding, thereby increasing the first ionization enthalpy of thallium. Following that is the group 4A elements. The elements of group 4A show a greater range of chemical behavior than any other family in the periodic table. Three of the five elements, carbon, tin, and lead, have been known since ancient times. The first member of group 4A, carbon, is a nonmetal, and the next two members, silicon and germanium, are metalloids. The rest are metals. Activated carbon is an even more finely divided form of carbon that is produced from the thermal decomposition of organic materials such as sawdust. Because it absorbs many organic and sulfur-containing compounds, activated carbon is used to decolorize foods, such as sugar, and to purify gases and wastewater. The group 4A form compounds in both the +2 and +4 oxidation states. For carbon and silicon, the +4 oxidation state is the much more stable one, as carbon dioxide is more stable than carbon monoxide, and silicon dioxide is a stable compound, while silicon monoxide does not exist under normal conditions. As we move down the group, however, the trend of stability is reversed. In tin compounds, the +4 oxidation state is only slightly more stable than the +2 oxidation state. In lead compounds, the +2 oxidation state is unquestionably the more stable one. The outer electron configuration of lead is 6s2, 6p2, and lead tends to lose only the 6p electrons to form lead 2 plus ion rather than both the 6p and 6s electrons to form lead 4 plus ion. The structures of the allotropes of carbon, diamond, graphite, fullerene, and nanotubes, are distinct, but they all contain simple electron pair bonds. Although all the carbon tetrahalides are known, they are generally not obtained by the direct reaction of carbon with the elemental halogens, but by indirect methods such as the following reaction, where X is chlorine or bromine. The metallic elements of this group, tin and lead, do not react with water, but they do react with the acids to liberate hydrogen gas. For the sample question, Which of the following are metalloids? Carbon, silicon, germanium, tin, lead, or fluorobium? The answer is germanium and silicon.
Let's now go to Group 5A elements. The nitrogens, also known as the nitrogen family, were named after the Greek word neon, which means choke or stifle. It refers to the suffocating property of breathing pure nitrogen gas. Group 5 elements consist of nonmetals, metalloids, and a metal. Nitrogen is the only non-solid element in this group. The atomic radius of group 5 elements increases down a group, and ionization energy and electronegativity decrease down a group. Also, the group 5 elements have 5 valence electrons in their highest energy orbitals. Nitrogen fixation can occur naturally when an electrical discharge hits air to a high temperature. The following reaction occurs. The electric arc process for nitrogen fixation was effective but expensive. The Haber process emerged as the most successful alternative, involving the reaction of nitrogen and hydrogen at high temperature and pressure with an iron aluminum oxide catalyst. Ammonia gets further converted into nitric oxide to nitrogen dioxide to nitric acid called the Oswald process and ammonium nitrate to nitrous oxide through subsequent reactions. Group 5A elements can react with halogens to form halide compounds. Hydrogen is an exception because unlike phosphorus, arsenic, and antimony, which have access to the orbitals in their excited states, nitrogen lacks these orbitals altogether. This limitation restricts its ability to form bonds with additional halogen atoms, therefore forming only trihalides. The trihalides and pentahalides react with water to form hydrogen halides and the oxoacid of the element. Nitrogen trihalides do not undergo this reaction because they are highly unstable and easily decompose in contact with water. Both nitrogen and bismuth pentahalides are unstable and hydrolyze differently. Group 5A elements can react with oxygen to form oxide compounds. Phosphorus can directly react to oxygen while most other group 5 elements typically undergo redox reactions. The oxides of nitrogen, phosphorus, and arsenic are acidic. Those of antimony are amphoteric, and the oxide of bismuth is basic. For test yourself part, you can pause the video to think about your answer. Let's proceed to Group 6A elements. Group 6A of the periodic table are known as chalcogens. The name chalcogen means ore former, derived from the Greek words chalkos, means ore, and gen, which means formation. The group 6 elements consist of electronegative nonmetals and metalloids, often found in metal-bearing minerals. The atomic radius of group 6A elements increases down a group, and ionization energy and electronegativity decrease down a group. Also, the group 6A elements have 6 valence electrons in their highest energy orbitals. Group 6A reacts with hydrogen gas to form hydrides except tellurium and polonium. Hydrogen telluride can form, but it's highly unstable and decomposes readily into its elements at room temperature. Polonium hydride might exist, but its resistance and properties are not definitively confirmed due to the radioactive nature of polonium. Chemically, oxygen is very reactive, forming compounds with all other elements except the noble gases, and apart from the halogens and some unreactive metals, this can be made to combine directly with oxygen under the right conditions. The oxides of sulfur and selenium are acidic, amphoteric for tellurium, and the oxide of polonium is basic. Then metals like sulfur, carbon, and phosphorus burn in oxygen to form acidic oxides. These can also be called acid anhydrides. They dissolve in water to form acids. All of the chalcogens form halides. Sulfur and chlorine can directly combine upon heating to form a halide. For other combinations, a redox reaction takes place. For test yourself part, you can pause the video to think about your answer.
Let us now explore the basic inorganic chemical reactions for the group 7A elements. Group 7A elements, collectively referred to as halogens, have their free elemental form consisting of diatomic molecules, excluding astatine, which is a radioactive element, and tennessine, which is a synthetic element. The chemistry of halogens are well understood. These elements have 7 electrons in their valence shell and can accept an electron to form an ion with a negative 1 charge. Moving down the group, atomic radii increases by 1 electron shell. Consequently, their reactivity decreases since the attraction for valence electrons of other atoms is also lessened down the group. This decrease also occurs due to the decrease in electronegativity. Therefore, the nucleus of atoms of larger atomic radii exhibits a weaker pull. This makes fluorine the most reactive element out of the group. A more reactive halogen will always displace a less reactive halogen in a compound. So we can demonstrate such displacement reactions using aqueous solutions of halogen-containing compounds. For example, when we add chlorine water into a solution of potassium bromide, a displacement reaction occurs, producing potassium chloride and liberating bromine. In contrast, when iodine is added to solutions of potassium chloride and potassium bromide, no displacement reactions occur, as iodine is less reactive than the other halogens. Halogens react with hydrogen, forming hydrogen halides, which are gases at room temperature. The direct combination of hydrogen gas and the elemental halogen to form hydrogen halide can only apply for chloride and bromide. In contrast, hydrogen fluoride is prepared by treating an appropriate metal fluoride with concentrated sulfuric acid. Analogous reactions are also different means of yielding hydrogen chloride, since chemists are usually more inclined to use aqueous solutions of these compounds rather than the pure gases. The bond strength of these molecules decreases down the group. Halogens react with alkali metals and alkaline earth metals to form halide salts. Reactions between halogens and these metals involve reduction and oxidation. Group 1 metals are oxidized from an oxidation state of 0 to plus 1. These alkali metals react vigorously with halogens to produce ionic salts. Group 2 metals are oxidized from 0 to plus 2, forming hydrated halides. Interhalogen compounds arise from the interaction of various halogens. There are 4 general types of interhalogen compounds, which are the diatomic, tetratomic, hexatomic, and octatomic interhalogens. The covalent bond between XY diatomic interhalogens has an ionic character, with the larger element X being oxidized and having partial positive charge. As an example, at 437 Kelvin, chlorine reacts with fluorine of equal volume to form chlorine fluoride. On the other hand, interhalogen compounds having the formulas XY3, XY5, and XY7 are formed through the reaction between pairs of halogens. Since halogens have 7 valence shell electrons, their outer shell is filled when 2 atoms form a bond. In contrast, when an unshared pair is separated, 2 additional bonding sites are available. For instance, if chlorine reacts with additional fluorine, chlorine trifluoride is formed. From their standard reduction potentials, it can be established that iodine and bromine lack the ability to convert water into oxygen because their reduction potentials are lower than that of oxygen. So as a consequence, iodine and bromine do not react with water. Conversely, fluorine and chlorine possess higher reduction potentials, thus having the capability to oxidize water. As an example, fluorine reacts with water vapor to form oxygen and ozone. Meanwhile, the reaction of water with chlorine proceeds very slowly. Let us recall what we just learned and apply our knowledge in the following situation. According to the halogen displacement rule, a more reactive halogen will displace a less reactive halogen from a solution of its ions. So, what is produced when bromine and sodium fluoride are mixed together? Since fluorine has the highest reactivity out of the halogens, bromine cannot displace fluorine from sodium fluoride. Let us now answer some problems related to the chemical reactions of representative elements. First, let's consider the following reaction. What do you think is the identity of element Z if it reacts readily with lithium? To solve this problem, let us first consider the ionic charge of the compound form. Since lithium is in group 1A, it has an ionic charge of positive 1. Using the crisscross method, we know that the numerical value of each of the ion charges is crossed over to become the subscript of the other ion. In this case, lithium has 3 as its subscript, indicating that the unknown element must have an ionic charge of 3, or negative 3. Based on our knowledge of the periodic table, we can say that an element of group 5A, or the nitrogen family, is the identity of the element. Lithium is an alkali metal and tends to form compounds with elements from group 5A, but the reactivity can vary depending on the specific element. For example, lithium reacts with nitrogen to form lithium nitride, and lithium reacts with phosphorus to form lithium phosphide. However, lithium's reactivity with arsenic, antimony, and bismuth is not as significant as with nitrogen and phosphorus. These heavier elements have different chemical properties compared to nitrogen and phosphorus, and lithium might not react as readily as them. Therefore, the identity of the element could be nitrogen or phosphorus.
Our problem solving number 2. Which of the following pairs of elements does not exhibit a diagonal relationship? A. Nitrogen and sulfur. B. Boron and silicon. C. Lithium and magnesium. D. Sodium and calcium. E. Carbon and phosphorus. You can pause the video to think about your answer. We have to remember that diagonal relationship are similarities between pairs of elements that are situated in different groups and periods and exist between elements in the second and third period that is diagonally adjacent. In the problem solving number 2, the pairs of element that does not exhibit a diagonal relationship is sodium and calcium, since sodium is in the third period and calcium is in the fourth period of the periodic table. For our problem solving number 3, arrange the following oxide in order of decreasing basicity: magnesium oxide, calcium oxide, barium oxide, beryllium oxide, and strontium oxide. You can pause the video to think about your answer. We have to remember that oxides go from basic to amphoteric to acidic across a period and become more basic as you go down a group. In problem solving number 3, you can see that the metal from oxides are given from group 2A. So we would expect that there is a decreasing basicity as you go up the group 2A. The answer for this question is barium oxide, strontium oxide, calcium oxide, magnesium oxide, and beryllium oxide. Now that we have explored the basic inorganic chemical reaction, let's do a recap. Representative elements are those elements from S and P blocks of the periodic table. Alkali metals are highly reactive with low melting points. Alkali earth metals are less reactive and have higher melting points than alkali metals. Boron group elements react directly with hydrogen to form hydrides. Carbon group metals react with acid to liberate hydrogen gas. Nitrogen group elements are known for its variation, but Haber process is a well-known reaction. Chalcogens tends to form ions with negative 2 charge upon reaction with highly electropositive metals. Halogens are quite reactive and they naturally occur combined with other elements. That's all for today, and I hope you learned a lot about the basic and organic chemical reaction of the representative elements.